Welcome everybody. It's a very great pleasure to introduce the next session on opportunities for harnessing mathematics. My name's Robert Leese. I'm Chief Technical Officer of the Smith Institute for Industrial Mathematics and System Engineering. You can read a little bit more about what we do in the material in the conference packs that you've all received. But I want to introduce the session by making a few remarks about effective ways of going about harnessing mathematics for economic benefit. What we find is that in the work we do, there are really four key elements that need to be addressed and need to be got right in some sense. And they are shown on this diagram here, and they are really the key to the core work that the Institute does, and also a lot of the other examples that we've already seen today. If you're going to harness mathematics effectively for solving complex problems, you need to really take account of these elements. Often they're not separated out in this sort of way. I think there's great advantage to looking at them very carefully. If any of these elements is weak, that can provide a weakness in the overall outcome. And equally, by thinking about these things as connected but separate items, you can ensure higher probability of getting successful outcomes. The first is modelling. We've heard a lot about modelling today, and I think the way I've heard the word modelling being used is consistent with what the view that I would take, namely that modelling, it provides the mathematical framework in which we think about difficult problems. Effectively, modelling captures a way of thinking. Absolutely crucial. The second we've also heard a lot about today, which is data and the way you handle data. Clearly, data engineering is going to become more prominent over time, simply because volumes of data are increasing so rapidly. So data engineering is something that must be taken into account, and how that interfaces with modelling. The third component is looking at algorithm selection and design. We've heard something about algorithms. They effectively are what glue the models and the data together. You need to look at what algorithms are available, what sorts of results they can produce, what sorts of models you need, what sorts of data you need to drive those processes. The fourth area is a little bit more bespoke, but absolutely crucial, is the way that you deliver or deploy this combination of models, data, and algorithms. Okay, and I'll say a little bit more about that in a moment. What we've found over the years in the Smith Institute is that these four elements are key to getting good outcomes. We work very heavily in security, energy, and telecommunications, but also in other sectors as well. And there are really some common themes that come through in all of that work. So some of the themes that we see coming up time and time again, issues around managing risk, around planning under uncertainty, and around optimization. These are cross-sectoral grand challenges that we need to have good approaches to. Let me just show one example. I think the telecom sector isn't really represented heavily in any of the other presentations, so I thought this would be a good example to give. This is a project that we've just completed work on. It's the broadcast incentive auction for radio spectrum licenses, which was held in the UK. The auction itself lasted just about a year. It completed in April of this year. And the aim was to repurpose radio spectrum that had currently been in use for TV broadcast and repurpose it for mobile data capacity. So this is trying to unlock economic value by repurposing spectrum from one use to another. In doing so, you can also improve the efficiency of spectrum assignments. Effectively, radio spectrum is a finite natural resource and so needs to be managed carefully, and the more that you can squeeze out of it, the better. All of this required some completely novel designs in auctions and also completely novel optimization procedures in order to get the right spectrum assignments. And this system diagram here is deliberately sized just so small that you probably can't read it. The point is that each box in that diagram, this is the system level view of that auction process, each box in that diagram contains the four elements that I had on the previous slide. Okay? And they interconnect in a reasonably complicated way to provide the overall outcome. Now, this could be easily a seminar in itself, but the outcome in a nutshell was that the US government ended up paying to TV companies a little over $10 billion in order to either relinquish spectrum licenses or to move to a different part of the radio spectrum, move their transmission to a different part of the spectrum. And the network operators paid something just under $20 billion, 50 of them in total, in order to acquire the licenses that had been freed up by the broadcasters. Okay, this was the largest amount of low-band spectrum that had ever been made available in an auction anywhere in the world. Now, what's the economic value of that activity? Well, one simple estimate is just to take the difference between those two numbers. Okay, so $10 billion roughly. That's an underestimate because it doesn't take any account of the value that the consumers of mobile data, in other words, all of us, would get from using the increased capacity in mobile services. So it doesn't include the consumer surplus in economic terms. So these are big questions. Very exciting to work on a project of this sort. Uses techniques in mathematics and general processes that we've seen already this morning. I just want to make one more point before I move on. In a sense, this diagram is unwrapping the tight connection of the four squares that I had earlier. This is a chain of technology readiness levels. John referred to these earlier on in his opening remarks. They were introduced by NASA in the 1980s, really, as a way of tracking technology maturity. So at the left-hand end, you have some basic principles, germ of an idea. And at the top end, at TRL, Technology Readiness Level 9, you have deployment, which in NASA's case would have been the successful completion of some mission. Now, that sort of chain, I think, can be usefully applied in all sorts of other circumstances, and I'm going to put forward the view that it can be applied to harnessing mathematics effectively as well, so that we have mathematical modelling at the lower ends, some sort of proof of concept or prototype design where you start to bring in the data that you need. In the middle TRLs, you have algorithms. You start to think about how you're going to make all of this a reality. And at the top end, you've got successful deployment. Now, there are 2 points that I would like to make about this. First of all is that this chain from 1 to 9 almost never involves a single group of people or a single set of experts from one end to the other. It will involve collaboration between organisations, collaboration between teams. So something that is crucial to making this chain work is making sure that you manage and plan those handover points effectively and correctly. That requires a little bit of foresight. The other point is that I think too often we have people who are sitting at one end of the chain or the other. And if you're sitting at one end of the chain or the other end looks awfully far away. And probably so far away that you can't really see clearly how you might, if you're sitting at the top end, how you might pull through mathematical ideas and make them useful, or if you're sitting in a university thinking about mathematical principles and models, how you might push those ideas out and get them taken up by industry. Okay? So I would urge you not to sit at one end of that chain or the other, but to sit somewhere in the middle so that you can get a much better view of what's going on. It's the way the Smith Institute tends to work. The FCC work that we did, the US Spectrum work that I just referred to, at different points of that we were down at level 2 and as far as level 8 towards the top end of that chain. It really is a very wide range that we have to cover. Those are my remarks. I'd like to now introduce the other speakers in this session. What we're going to do is there are going to be 3 other speakers. I know there were 4 named in your programme. Mayesta Ewer from NATS isn't able to join us this morning at short notice. What I will do is let the speakers introduce themselves. I'll just very briefly introduce them at the moment. And then at the end of the presentations, which will follow on seamlessly one from the other, the 4 of us will come back up and we'll sit up here and take questions together. So if we could save questions until the end of the session. I think that will allow more people the opportunity to ask questions. So our three speakers in order are, first of all, Malcolm Skingle, who is the Director of Academic Liaison at GSK, and then Andrew Randewich, who's the Chief Scientist at AWE, and finally Mark Taylor, who's the Director of Strategy and Global Research at Dyson. So, Malcolm, over to you.
Thanks very much. Thanks very much for the invitation to talk here, but although you can see from the title slide there, I'm probably the least qualified with my O-level maths, which is the last time I took the education of sums seriously. I struggled to put this talk together primarily because maths is absolutely pervasive in all that we do, and to actually select an example or a few examples was quite difficult. I put an email out to the people that are involved in stats and maths at work, and I was absolutely inundated, but I know I'm preaching to the converted here. In the first half of my career, I was a scientist, a neuroscientist, and actually the labs that I worked in generated single point data results to day-long experiments. And actually the interpretation of those data were fairly trivial by comparison to what we've got today. What we've got today is we've got automation, we've got robotics, we've got millions of compounds that we screen, we've got chemical analytics, we've got networks. And this is all generated in such high volume that actually the human brain can't get its mind around it. We need clever analytics and stats to cope with that. And we obviously need visualization techniques. We need stats that, frankly, I just want the answer at the end. I need someone else far brighter than me to actually to get to that. But I think it's true to say that for all of our scientists that we don't think enough about the analysis of our data. It's calculated that less than 0.5% of all data is ever analysed and used, and I think that's particularly true in my industry. Sometimes experiments are repeated rather than old ones being reanalysed, and I think that we actually need to upskill all of our STEM scientists across the board to actually pull more information out of the experiments that they're doing. There are 4 big decisions that you have to make in making a medicine, and when you consider that it costs a lot of money, more than that's a low estimate there of $1 billion for to actually produce a medicine. You have to decide on which target you're going for. You have to get enough evidence for that biological target to actually want to invest in then trying to find a molecule, which is the second big question. So either a chemical or a biological reagent. And then once you've kind of got the most selective compound that you think is going to get to where it needs to get, i.e. to cross the blood-brain barrier if it's a CNS drug or to various parts of the body that you need it to get to in sufficiently high concentration to bring about an effect, you then have to determine, well, what's the killer clinical biological experiment which is actually going to give you enough confidence to invest millions of pounds in demonstrating at a late stage the clinical effect in a clinical trial. And when I started in the industry, it was shown that molecule was significantly different to placebo, and of course nowadays it's against gold standard, and you have to go through various not only regulatory hurdles, then you have to show demonstration of value in the real world with real world data, and you have to get through the NICE hurdles in the UK and various other authorities around the world. So those 4 big decisions are absolutely underpinned by solid mathematical analysis at every stage, and that is evolving. We now do different types of trials where we would actually change a study as we were going along depending on the data that we're actually getting back. So here's my first example, and that's human genetic evidence for approved drug indications. So we know that for drugs with human genetic information, you're twice as likely for that molecule to proceed through the drug development pathway. And conversely, those that haven't got genetic information are more likely the ones to be the ones that bomb. And that's true at every stage. Now, it's fine if it's a monogenetic rare disease and you can do various experiments to take that disease out in transgenic animals to give yourself greater confidence. But most diseases are not like that. They are multi-gene. You have differential gene expression, for those of you who are familiar with that. And you'd have the control differential gene expression profile, where you've got hundreds of thousands of genes. And then in the disease state, you'll have variations. You might have 100 go up, you might have 100 go down, you might have some remain the same. And then you give a molecule, and then you look at the gene expression profile again, you see it change. I think it was a few years ago, there's something like 15 new genetic gene associations being identified every single week. Now, that level of complexity and those networks and those signalling pathways, the human brain cannot get its head around that. You need data mining techniques, you need very, very clever maths to get to that. And this is scalable. You know, it's gone from when I started in the industry, as I said, with very low numbers to absolute massive numbers. Now, everything is multiplexed, everything is big data. So this is one of our collaborations, and this is the Open Target, so-called Open Target program. And this is where we have a couple of dozen of our scientists actually sitting in Hingston at the Sanger Centre and the European Bioinformatics Institute. And what we do is we effectively mine all of the public databases that are out there, so databases on the reactome chemical reactions, transgenic animals, all the gene sequencing information, all the chemical databases that are publicly available. And what we do is we meld that data with our own experimental data, which is proprietary, and we stick that in something what we call the target validation platform. And we actually contest the hypothesis in silico before we spend millions of pounds on taking that to the next step. And this is open. You can actually go to that and you can actually use this yourself if you're a competitor pharmaceutical company, because as an organisation, we believe that the more transparent you are about putting out the non-proprietary, getting as much information out there as possible, the more likely you are to get it back. And that's completely different to how our industry was, say, 10, 20 years ago. Now, once you've got the confidence to go with a particular biological target, and you think you have enough evidence to place that bet, to go for it, then it's down to screening. And that's when the numbers really start to get large, once you finish with the genetics and the validation. Because for a typical screen, we'd probably screen between 2 and 3 million compounds against, be it biological or NCE. And there are various types of screen, but a general screen would obviously use robotics and automation. We would get possibly dose response curves for each of those things, and then you would then want to compare the physicochemical properties of the molecule, i.e. has it got the properties to get across certain membranes to get to the tissues you want to get it to, and also is it like to have off-target effects, i.e. side effects. And you've got that massive information and you're trying to find that needle in the haystack to see which bet you're going to place to take the compound through. So the data from these types of experiments would go into data flows like this one, where we would pull together multiple bits of software to get to the end product. And the whole purpose of this is to take an absolute mass of data and to dumb it down to a level so that a scientist can look at it and actually determine whether or not that's the molecule that we're going to go with. And when I was researching for this talk, frankly, I didn't even know we did some of the, we had some of these software packages that we have and that we use pretty routinely because it is all dumbed down for us. If I move on to clinical data, I mean, physiological parameters are now being recorded in real time and analysed even by Joe Public with their Fitbits. This is going to increase. I was talking to someone at dinner last night who is from a CRO, and he was saying that in the clinical trial you typically have 1 million data points per patient. And in a few years' time that will be 1 million data points per patient per day. So it's just scaling, absolutely scaling up. So this here is obviously the simple stuff, the heart rate, respiration rate, stress, number of steps, etc. But you would do that before and after medication. So you'd be comparing those data and you'd be comparing it in real time. There is other software to determine whether or not you'd actually taken your medication, because we have a lot of issues with adherence where people actually go and get their script but then don't actually take it, and certainly often don't take it on time. So the data are getting larger, they're getting more complicated, and we are absolutely trying to accelerate the discovery. It takes a long time to develop a drug. We're trying to get that time down, because obviously time's money. The patent clock is ticking once you've actually filed that patent for your molecules. We're trying to accelerate the discovery and development of new medicines by capturing the full experience, the so-called real-world effect. So I've already mentioned the digital devices, the Fitbit. I mean, obviously there's genomic information. 23andMe, you can all get it done. You can look at your ancestry. You can determine which risk genes that you have. I personally, I think the biggest problem and issue in this space is actually getting the public on board with that. I personally have never had a sick day since tonsillitis when I was 14, never had a day off work, which I'm proud of. I'm going to go down big time with something. I would rather have all of my information on a chip or on a watch or on something, so that when I need medical help, they've got all the information they require to be able to help me. We heard from Dunnhumby. I've been doing it for years, looking at our spending profile. But wouldn't it be powerful? In fact, I used to know the former chief exec of Dunnhumby, and we had a conversation many years ago about, well, if you had the illness data, you had the electronic health records, and you had the longitudinal profile of health, and then you had the consumer data, you know, how many donuts, how much wine, how many cigarettes at the bad end, or conversely at the other end, you know, how much sports equipment you were buying and whether you were a member of a gym and whether you actually attended, how powerful that would be. And that's a little bit Big Brother, probably too Big Brother for the public. But frankly, you know, if you had that data, you'd be better, coupled with the genetic information, you'd be better able to identify. And some people want to know, some people don't want to know eventually what they're going to get with. But most people actually do want to know, because they want to do something about it if they can. Environmental data. In this room, there was a lecture about a month or so ago, which was showing how you could correlate postcode with the development of lung disease, asthma in children. In fact, it might have been downstairs, but it was at the Royal Society. So if you have a look at the inner city regions and the kids going to schools there, and you have a look around Heathrow, where obviously there's a lot of traffic and a lot of fuel dumping, then you can see that the development of lungs in those kids is not as good as the ones living out in leafy Oxfordshire. And social media, of course, which is becoming increasingly important in all of our lives. And social media, you have patient groups who self-report and in fact self-aggregate, particularly in the rare disease area, which is a good thing. So you can mine that information as well, and you pull all this information together, and you get quite a strong profile of the likelihood of someone's going to get a disease, and once they've got a disease, whether or not they're taking their medication, and what their likely health outcome is. So finally, and I'm preaching the converted here, you know, when you come along to things like this, we will increasingly use complex data analytics, and it will certainly help us to develop new medicines. There's some quite ambitious projects. There's one in the US at the moment called Atom, where we're trying to absolutely compress, using in silico methods and data analytics, the time taken to develop a medicine. If we're thinking about personalised medicine, obviously we're going to have to get much slicker at it than we are now. We'll need to certainly train more data scientists and hire mathematicians to curate and analyse data. I mean, the comment earlier about, you know, how much you pay them, you know, is a valid one. I think that what will happen is that we will train a lot of people in this space, in data science and in mathematics. And I think that the sectors will be in competition, and we'll all want them for submarines, for drugs, for banking, for whatever. And I think that we're going to have to put a lot of people in that hopper to make sure we get the right people out the other end. And we also need to upskill our STEM scientists to cope with the tsunami of data that is now upon us. We're just about to embark on a 3-year program at GSK to do just that. So we want our STEM scientists to think more carefully about how they're doing their experiments and how they're extracting data and the maths and the analytics of that at one end. And then, of course, we've got the more geeky end of the people who, that's all they do, which is data science. And we need both in the organisation. And my final slide is just, none of these slides are mine. I plagiarise them from these people. Thank you very much.
There we go. Okay. So upgrades in computing power have been happening now for decades. We have particularly powerful tools these days. Seductively powerful. You mustn't trust computational physicists, because I'm one. We produce calculations these days that are beguiling and very believable. You do need to underpin things with some kind of experiment. But actually, you can rely a lot less on empiricism than you could in the past, and you can save a lot of money by using modern modeling tools and high-powered computing. So lots of technology areas exploit that. I'm going to talk about the nuclear deterrent. And then I'm going to worry a bit about how it's going to be more difficult to exploit some of these things in the future. So mathematics was always at the core of the nuclear deterrent. This chap is William Penny, later Lord Penny. He was a mathematics prodigy who was part of the Manhattan Project and came back and was tasked with setting up Aldermaston. And he did, and it was all very successful. But at the time when he worked first, there were no computers. So this is a log graph on the y-axis of floating point operations per second as a function of year. And each of the red spots is a computer that Aldermaston purchased. And I've got pictures of some of them, but not all of them, just because of the space. So you can see an initial surge in computing power, began to plateau, then Seymour Cray came along, invented vector processing. Things got better for a while, and then began to plateau. And eventually we realized the best way to get performance was just to lash lots and lots of simple computers together and do massively parallel programming. And today we're up in the petaflop regime, petaflop being 1,000,000 billion floating point operations per second. So I'm going to keep the axes exactly the same, and I'll take away some of the computers and just put some other things on. So 1952 was the first UK nuclear test. That happened before we bought our first supercomputer. So first myth busted, you do not need a computer to design a nuclear weapon. By the time there was a thermonuclear test in 1958, we had got rid of the Ferranti, and we were just installing the IBM 704 mighty beast that it was. And then in 1991, nuclear testing stopped. And actually, it's after that you need a big computer. Just for reference, I put a desktop PC level on there. So your typical desktop PC today would outperform a mid-90s supercomputer and is certainly more powerful than what we had whenever the last nuclear test happened. In fact, probably your mobile phone outperforms the computer we had then. So why do I need a big computer? Why is it challenging? Well, there are no nuclear tests anymore, more than 26 years since the last test. You might say that we know nuclear weapons work, but actually materials change with time. If you leave anything lying about for a decade on a windowsill, its material properties will not be the same at the end of the decade as they were at the start. So there are challenges in order to understand and keep the product guaranteed safe, guaranteed reliable, and also to fulfill some of our other missions in nuclear security, so treaty verification, trafficking of nuclear materials, arms control, and those kind of things. So certification is done by calculation, a mathematical formulation that we discretize, and then we, by a large computer, run the program on the computer. We do still underpin with material models for data and for validation. And typically, we're driven to an explosive test facility and then something to make material hot and dense, because that's what it's like in a nuclear weapon. But those experiments are really expensive, seriously expensive. Flight trials are eye-watering. The UK just doesn't really do that. At the top of the picture, I've got the artist's impression on the real-life Orion laser at AWE. So that's sort of a £200 million class facility. We also access the National Ignition Facility laser to make material hot and dense in the US. That's kind of $4 billion, much bigger again. Because of some of the costs, we look for collaborative efficiencies. So in the 2010 Defence Review, an economy package was agreed, so we share an explosive test facility now with our French colleagues. And engineering equally drives experimentation. So our product needs to be able to survive for many years, so you have to model from time scales that are very short through to very long. We use shake, rattle, and roll environments, centrifuges, and use those to validate large finite element models on stresses and strains and vibrations in the product. Computational physics. Typically, we're doing compressible fluid flow, so simple enough equations to formulate and discretize, but we do that coupled to both Monte Carlo and deterministic transport models for neutronics and for radiation, and several other bits of physics in the code as well, typically multidimensional. So you start to have to make approximations. You have to throw all the tricks you can at the problem. So at the top, there's some examples of adaptive mesh refinement where we have targeted the fine resolution mesh at the areas of the problem where it's needed and left less resolved some of the other areas in the problem. And as shocks run through the mesh tracks where it needs to be. But all of those complications make the problem more difficult to run on supercomputers. Modern distributed parallel supercomputers require you to take the problem, decide what parts of it are going to be held by which different processing units, and then to periodically communicate the boundaries between the two. So we do have some of the largest computers in the UK to tackle those problems, typically tens of thousands of cores. It used to be you had a supercomputer where you said, my supercomputer can keep up with the whole planet, each person having a calculator and doing one a second. These days, every core can do that, and we have tens of thousands of them. And then you have to have the ancillary things like fast networks, large file stores, the ability to visualize and cut the huge data sets, high-end workstations, in order to deal with some of those, some of the data that the codes produce. So just to come back to this chart, that kind of sounds okay, but the question is, what comes next? And it's actually quite an uncertain future for HPC. We've been at sort of 3 gigahertz limit for quite a long time now. The speed's not going up because of dissipating heat, so you start to worry about floating point operations per watt rather than floating point operations per second. One solution is to switch to models where you use many, many compute cores, lots and lots and lots of them, but wind back to really slow clock speeds. That was IBM's Blue Gene Q. That's kind of dead-ended, but it is a world now where we are going to have many more cores in the computers we use. We've seen dual-core, quad-core. Typically, we're now buying 12 and 20 cores as the default number on our platforms. So you need a lot more parallel scalability. And probably a model where you have islands of shared memory and communication beyond them, so layered protocols. There's a thing called the memory wall. The difficulty is not getting a chip that can do more floating point operations. It's being able to get the data to the chip fast enough to do those operations. And that's why we have lots of levels of cache memory in the chips, highest performance, lowest amounts of memory at the bottom. And more levels of cache will come in, but are difficult to exploit. So we'll move to new paradigms, new ways of coding. So the risk is that we can't adapt our numerical methods in order to use computers that have things like many, many cores or accelerators like graphical processing units, GPUs. And you're forced to buy very simple, inefficient computers, and that matters. For a sort of an x86 type supercomputer, if you want a petaflop, it runs on about a megawatt of electricity, and a megawatt will cost you £1 million a year. So it's expensive to do computing if you can't find ways to be cleverer. So the mitigations are many-fold, but part of it is to buy and test chunks of advanced architectures rather than simply living in the world of the past. You can do modeling of how different kinds of algorithm will work best on what different kinds of architecture, and some of that is important as well. Collaboration is key, actually, and if you can exploit external platforms through your collaborations, then that matters as well. What isn't an option is to do what we did in the past when Craze came along, which was to completely rewrite the code for every single supercomputer that we bought, because it's just too hard, there's too much. So not all computers are the same. GCHQ streams a lot of data, whether it's all about resilience, periodicity, getting a forecast out. Formula One limited by maximum theoretical floating point operations per second. So actually they would tend to buy a very old supercomputer that they could exploit to the absolute limit. Engineering is memory limit, as I've said. Ray tracing is embarrassingly parallel, so it's okay for cartoons. And science I've talked about. So the aim overall then is to cost effectively provide HPC for calculations. So it's the large scale hardware, but it's also the people. So in this room, I'm not going to diss mathematicians. I will say physicists will write an algorithm that solves exactly the problem they want to be solved, but runs like a dog. The computer scientist will write an algorithm that runs beautifully but solves no problem known to man. The key to all of this is to get everybody to work very closely together, hand in hand, in order to develop the tools and the solutions that run on those tools to address the mathematical problems that we need to in order to do our business. And it's a balance. It's a balance between people and hardware. So I summarise just with what I said at the start.
Some questions. If you wait for the microphone to reach you before you ask your question, that would be very helpful. Thank you.
Thank you. This is a question mainly for Malcolm. When I was during the last presentation, we saw some product that was designed completely in the computer. I was wondering, where are we designing drugs, especially designing antibodies? Once we know the 3D structure of the protein that we are targeting, how far are we into designing the antibody and the genetic sequence behind that? And if you could comment on what are the challenges today and the potential opportunities for collaborations with supercomputer and mathematicians and other scientists. Thank you.
Well, there's a few questions in there. Where are we with modelling? I think every part of our industry is looking at modelling and using mathematicians at the moment. Potential for collaboration. I proudly say that we collaborate more than any UK-based company, and I know that just through discussion through CBI and the ABPI, where we actually collate the data. And if you look generally, if you look at the Downing review, the last ref impact case study, everybody always talks about Rolls-Royce. You know, I think they had 112 examples. We had something like 152. We were easily the highest, and pharma were quite. I think 15 of the top 40 companies for collaboration were pharma companies in the UK. So obviously we've been doing it for years, because that goes back 20 years. I think the rate of pace of change in our industry is matched only by the number of collaborations that we've got, and that's globally. So I came out of science running a research group 20 years ago, and it was me and half a secretary used to look after all the academic collaboration programs for GSK R&D. I've now got a team of a dozen, half here, half in the US. We do about 700 collaboration agreements a year globally. It used to be that 20 years ago, it was something like 3 or 4% of the UK R&D budget would go outside these shores. Now it's about half. That's how quickly we've changed. We're going to get our science wherever we can, and we're going to collaborate with people who want to collaborate with us. And I would say that, you know, I meet a lot of very, very bright people, often smarter than me. But once they start collaborating, it's never the money that's the major driver for the collaboration. It's always they want to get access to our smart people, to the technologies that we're pulling together, because we're going to take the best technologies that we can to help us drive the process. And modelling and maths is a very big part of that.
Yes, Vicky.
Vicky Pope from the Met Office. I had a question for Andrew. There were many links, I think, to the problems that we're facing in meteorology as well. And I just wondered if you had any idea where the breakthroughs are going to come in making better use of the next stage supercomputing technologies, because we've got very similar challenges.
Yes, we do talk. Some of the climate change work in particular is very similar to the kind of problems we have, where you have different things you're modelling, different algorithms that all have to be coupled together, and it makes it a complicated thing to get onto the next generation computers. One approach is to have a spectrum of different platforms. So the really difficult multi-physics applications can sit on relatively simple hardware and target the more advanced accelerated hardware for some of the algorithms that naturally scale better because they're more to do with single material properties and the like. So it's sometimes a balanced approach is the best way to get there. But at the moment we are facing the fact that rather than develop new science for a while, we are going to invest a few years in refactoring our code, not in order to make it particularly tractable for any one computer, but to make it generically slicker on many platforms. And that's an investment that we're just going to have to face.
Here's another question right at the front.
Thank you. I'm Susan Greer and I came as a teacher for teaching preparation. So thank you so much for such an interesting day and also stimulating. Does the panel, and please, I hope you don't mind me asking such a question, because it came up yesterday, I was given a memory card, and in order to format it, I've had to delete the data, which was quite a big decision for me because I didn't know whether I was deleting some work which somebody had already done for me. What's your opinion about deletion of data in new equipment? And thanks for listening.
Shall I take that one? When you delete files, they're typically not actually deleted, even when you reformat. So one thing to be aware of always is that if you get some software, and you can buy it for yourself, if you accidentally delete the photos from your phone, you can get some software that will miraculously recover them all, even though they were apparently gone. So what's deleted isn't really deleted until it's been written over many times. So it may still be there.
There's one more question right at the very front. Thanks.
Hi, Lucy Rifle-Smith, University of Cambridge. I have a particular interest in mathematics curriculum at the moment, so I wanted to ask the panel, really, what do you consider to be the current strengths and weaknesses of the UK maths curriculum from your point of view, and would you make any changes if you could?
Well, that's a good question. Shall I have first go at this? I'm still involved in undergraduate teaching. You're talking about undergraduate curriculum?
Well, I'm talking about all the way through, actually, school mathematics all the way through to university.
One thing I have heard from teachers is that they find it very difficult to persuade their strongest mathematicians at school to pursue mathematics at university. So I think if you're good at mathematics at school, it's a subject that, in a sense, you find easy, but I think very often you find rather dull. And if anything can be done to spice it up a little bit at school, I think that would be a great thing. I think in terms of what gets taught in universities, with the way that technology is moving, I think universities would do well to have quite a rapid cycle time when it comes to updating their curriculum over the next decade or so, to keep pace with things like the rise of data science.
Not all schools are blessed with a lot of teachers who feel competent to properly teach higher level mathematics, and that's an issue I would observe. So whatever curriculum you set has to be realisable by the schools, and it's a balance between having the teachers. Maths, I think, is a little bit blessed compared to other subjects in that the curriculum actually already has levels, so there's advanced maths and further maths exams that are there that will stretch the best pupils in a way that physics curriculum perhaps doesn't have some of those advantages.
I don't know if Adrian Smith is here. I noticed his name on the attendance list, but he reported a piece of research he'd done recently where to fill the gaps in mathematics teaching requirement in UK schools would require something like 20% of mathematics graduates to go into teaching. It's a huge percentage. There's a kind of real need there, I think.
I'd add a point there that I've got two young boys, 10 and 12, and they're just mad on coding and software and apps and things like that. So I think anything that could link mathematics without dumbing down the key principles into the children's interests, I think would be really helpful.
Maybe time for one more question before lunch. Julian.
So we discussed in the previous session the question of mathematics in schools and motivation and so on, and this different percentage of people staying on to do maths in France and the UK. So one of the things, of course, is that we still have essentially a specialised A-level. I mean, and a lot of people feel that they want to do a broader range. And I wonder, I mean, clearly, other countries which, as it were, keep doing mathematics with a lot of other subjects don't do badly at the end. But funnily enough, universities in this country have always put the big pressure on to continue highly specialized A-level. And if the mathematics community would say, well, actually, we think you should do maths, but you should be doing it with a wider range of subjects, maybe that would help. I don't know what your comments would be.
I'd agree with that.
Yeah, me too.
I'd wholeheartedly agree with that. Yeah.
That's a good point to end on. Total agreement. Thank you very much. Very good. Well, thank you for those questions. I think we've reached lunchtime, so we should certainly break for lunch. If you could thank all the speakers again.